students, we're going to go over how to draw particulate diagrams in this video. Particulate diagrams are very useful in visualizing the content that we're teaching and representing what's actually happening on a macroscopic level, okay? So when we represent our particles, usually we use circles to represent our particles, but you don't have to. You can choose to do different shapes because the important thing is to choose a different way to represent each type of particle in that reaction. So that could be, depending on what the reaction is, it could be a different atom, it could be a different compound. You could use different colors. You could shade one and leave the other one unshaded. You can use different shapes, but as long as you make a key to let us know which substance or which particle each one represents, okay? One thing to keep in mind while you're drawing your particle diagrams is to represent the state of matter as best as you can. With solids, as you know, those are tightly packed together and they're going to be drawn at the bottom of your container. With liquids, they're a little bit more spaced apart than your solids, but also those would be drawn towards the bottom of your container. Gases, however, those are going to be really far spread apart and you want to fill your containers. You want those to be all around your container. With your aqueous solutions, we are going to talk about that either in intermolecular forces unit or in our solutions unit. So those will be coming up soon. So we're going to look at this one on page 9. When nitrogen gas, which are the dark spheres, and chlorine gas, which are the light spheres, react, they form nitrogen trichloride. So we want to look at our balanced reaction first. So we have N2 plus 3Cl2 is yielding NCl3. So we see here what are the is on the reactant side. We've got the dark nitrogens and we have the light chlorines. So I'm going to choose to use this red color to represent the nitrogens, and I count and I see that I have 8 nitrogens there. I'm going to use blue to represent my chlorine, and I can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules. So that means I have 18 atoms of chlorine. Looking up here at my balanced chemical equation, I can see that 8 nitrogen atoms would make 8 NCl3s because it only needs 1. But because NCl3 needs 3 chlorines, I could only make 6 with the chlorine. That means that chlorine is going to be my limiting reactant. So I'm going to first draw 6 nitrogens, atoms that are going to be part of my nitrogen trichloride. I see though that if I draw 6, I'm going to have 2 of these left. So I'm going to draw 2 that are still bonded together because they did not form one of their products. Then each of these is going to need to have 3 chlorines with it. So I'll go ahead and draw 3 chlorines on each of those particles. It doesn't matter how you draw it. Notice that these are touching because they're part of the compound. All right, and that would be my particulate diagram for the product side. I still have this here present because that would still be present in the reaction vessel. It didn't have anything to react with, so we can't get rid of it. We need to conserve the mass. That means our chlorine was our limiting reactant here. I'm going to let you all do this problem on your own if you need some practice to find the percent yield. And I'm just going to move on to the next particulate diagram. All right, so let's take a look at this one on page 10. So we're trying to determine the particulate, or draw the particulate diagram for the reactants and products when 4 moles of zinc sulfide react with 8 moles of oxygen. So I'm going to make, now I don't know what happened there. I'm going to make zinc red. I'm going to make sulfur blue. Whoa, what happened? Okay. Hang on, let me redo that. Whoopsie. I'm going to make sulfur blue. I don't know why that is in red. Let me stop sharing for a second. Let me share back this again. Wants to keep my annotations for some reason. I'm going to make sulfur blue. Sorry, I don't know what is happening here. It's my colors. All right, I think I fixed the problem here. So I said that we were going to make the zinc red. We are going to make the sulfur blue. And let's choose this fun purple for the oxygen. So it says that we're reacting 4 moles of zinc sulfide with 8 moles of O2. So I'm going to go ahead and draw my O2 right now since I'm already in purple. So I got to make 8 of these. So that's 3, 4, 5, 6, 7, 8. I'm going to switch to my zinc sulfide. So I've got 4 moles of zinc sulfide. I just did all of my reds first. I'm going to come back and do my blues. I'm making this tightly packed together down here at the bottom because it's a solid. All right. Over here, we want to see how much we can make, how many products we can make if those are our reactants. Okay. So with the zinc sulfide, it looks like since the coefficient of zinc sulfide is 2, and we can make 2 zinc oxides and 2 sulfur dioxides, if we have twice as much zinc sulfide present, we can make twice as many products. With this oxygen here, we have, let's take a look, more than twice as much, because if we had 2 times this, that would only be 6. So we have more oxygen than we actually need. We would need 6 of this to react completely. So oxygen is going to be our excess reactant. Zinc sulfide is our limiting. So I know that I'm going to have some extra oxygens. I'm going to have 2 extra oxygens here. So I'm going to have some zinc oxide, 4 moles of my zinc oxide, and it's a solid, so I'm going to put it down here at the bottom. I'm just going to do the oxygen first, and then I'm going to come back and do the zinc. There we go. And it says that I'm going to have 4 moles of the SO2. I'm going to go ahead, and that's a gas. I'm going to put it up here in the air. I'm going to put those 4 here, and then I'm going to come back and do my oxygens. I almost chose the wrong color. So I'm going to add 2 oxygens to each of those. And so that's what my particulate diagram should look like. I need to have those extra oxygens because those 2 molecules did not bond. All right, let me clear that drawing. We shall move on. I'm going to let you guys do this problem on your own. Actually, I'm going to talk about this one. So first off, our reaction is already balanced. Now, when you look at this, it says, what is the percent yield if the quantity of the reactants is sufficient to produce 0.86 grams of Cl2O, but only 0.71 grams is obtained? So we're already balanced. Like I said, when you look at this, it tells us that it was sufficient to produce 0.86 grams of Cl2, but only 0.71 grams is obtained. Which of these 2 numbers would be our actual yield? Our actual yield would be this one here, because we only obtained, can't spell yield, we only obtained 0.71 grams. Then the question remains, what do we do with this number? Do we do stoichiometry? No, because this is telling us that we could produce 0.86 grams. So that means that is our theoretical yield. So when we calculate our percent yield, we would take that actual, I forgot it now, we'll take that actual 0.71 grams We're going to divide it by our theoretical and times it by 100. Okay? The answer's in the packet. All right, so I'm going to let you guys tackle this question, and I'm going to get to this particulate diagram. So it says, draw a particulate diagram for the reactants needed to produce 6 moles of CO2. So we need 6 moles of CO2. Usually it makes 3. So that means we have twice as much CO2 as the reaction would call for, which means we need twice as much of these things. Okay. So here, I'm going to pick, well, I got to make a key, of course. So I will make the arsenic blue. I'm going to make the oxygen red. And I'm going to make the carbon black, like charcoal. So I'm already in black, so I'm going to go ahead and do that first. So we need 6 carbons. This is a solid, so it would be tightly packed down here at the bottom. I need 4 diarsenic trioxides, and that is a solid, tightly packed down here at the bottom. So I would need 2 of these and 3 oxygens. I need 2 more of these and 3 oxygens. I need 2 arsenics and 3 oxygens. And then 1 more, because I need 4 of these total, 2 arsenics and 3 oxygens. All right, and that should be what we would need in order to make 6 moles of carbon dioxide. So that's it. If y'all have any questions about particulate diagrams while you're working on your class kit, just raise your hand, let me know, and I'll come and check it out. All right, thanks everybody.